Today, we're fortunate to have Yuan-Ming Liu talking from Ohio State University. Topological materials is really sort of a revelation with the discovery or a realization of the Berry phase in the 1980s, and it takes a long time for the theorists to realize they were forgetting this important phase term that they canceled out in the earlier equations. And so it's really been a revolution in solid state physics when you realize that you really do need to keep in account these phases that look like you have hidden magnetic fields tucked into your material with properties you didn't expect before. And so Professor Liu's been working in this, the theory of these things in this territory. He'll be talking, excuse me. So he got his PhD from Boston College back in 2011, went on to a postdoc at Lawrence Berkeley Lab, left there at 2014 and started up at Ohio State University 2015 and got promoted 2019. So I look forward to your talk. Thanks very much for coming.
First, I'd like to thank the organizers for giving me the opportunity to speak here. It's a pleasure to be, virtually be back to Boston. Yeah, so today I want to talk about a new family of topological excitations in solids, which are so-called topological magnons or spin waves. In particular, I want to talk about how can we possibly engineer these topological spin waves in materials using different things such as light and electric field or magnetic field. So I actually, I have two screens with me, and the other screen I have the chat box and the question and answer open. So feel free to ask questions using those channels anytime. I should be able to keep track and then answer you immediately. And I wasn't so sure about the audience, so I prepared a rather pedagogical talk. And I certainly welcome all kinds of questions along the line. So yeah, so the outline of the talk is the following. First, I want to explain a little bit motivation. What do I mean by topological magnons and why are we interested in them? And second, I want to give you actually a brief introduction to the theoretical understanding of topology in spin waves. How are they compared to, for example, topology in electronic band structure, as we are more familiar with in the context of topological insulator and topological superconductors. After that, I want to actually go into a bit more into material side and want to talk about some specific material. For example, I want to focus on a certain family known as transition metal trifluorides. I want to talk about how can we engineer, in that case, topological magnons using external fields. And in the end, I also want to discuss another family of topological phenomena inside these quantum magnets, which is when we periodically drive a quantum magnet using, for example, lasers. Can we engineer some new kind of topological excitation? And these new excitation are known as flow-head topological magnons. I want to talk about those systems. Yeah, so that's the plan. I want to start by giving you some motivation about this type of study. Why are we interested in topology inside spin waves or magnons? So we all know that spintronics actually has played a very important role in our daily life right now. So in particular, after the discovery of Albert Fert and Peter Gromberg, after they discovered the giant magneto resistance, this effect has been used a lot in many electronic-based devices. So, for example, in our daily life, the hard drives and RAMs, the basic idea behind them are actually this giant magneto resistance. So the idea is the following, is that we know that electrons, in addition to charge, they also carry spin. And this spin, we can use them to store information in certain devices. In particular, this information can both be stored and read out using this giant magnetoresistance. The idea is the following. Imagine you have actually two regions. These two regions have different polarization of the spin. So if the polarization of the spin are opposite in this case, then if you measure the current going through between the two regions, because the spin, there's a mismatch between the spins, the current is small. On the other hand, if the two regions have the same spin polarization, you have a larger current. So in this case, by switching the spin of the system, you can also change significantly the resistance in such a system. This is known as giant magnetoresistance. So in this case, by measuring the electrical resistance in the system, you can effectively measuring the spin polarization of this bottom region, if we know that top region have the same spin polarization. So in this case, we can read out the information stored in the spin by electronic signals. And this is basically the idea behind the many memories and hard drives. So this approach, as we can see, actually, when we read out this information, we need to measure electric current. So there are certain intrinsic issue about this kind of electronic device, is that they suffer, for example, heavy ohmic loss. So there's a lot of joule heating in that kind of devices. So that's what motivated people to think about a device based on purely spin, but not charge degree of freedom. And these devices, we call them magnonic device. And this kind of area is also known as magnon spintronics. Instead of using electron, we use magnons to study, we use property of magnon to store information. And there is certain advantage for this kind of applications. First of all, I have to talk about that there is no ohmic loss like the case of electron, because the charge degree freedom does not enter in this case. It's only spin that enters. And the second advantage is that there's a relatively longer coherence length when we talk about magnon compared to the case of electrons. Roughly speaking, for these magnon spintronics, the typical length scale in such a system can be as high as centimeters in certain system. In contrary, for spintronic device based on electrons, where the information is stored by the spin of electrons, the coherence length in that system can only be as large as micrometers. So in this case, the system actually enjoys a longer coherence length in pure magnon devices. In particular, in these magnon devices, what is used and is mostly the so-called magnetostatic surface wave, or MSSW. So these are the waves of spins localized on the surface of this material. And this is what is used to store information and transport information in these devices. So, for example, this is a review which gives you some idea about how to build these magnonic devices in various systems. But there is also some problem related to this magnonic device, and these problems are mostly two sides. So first major problem is about damping. This damping really resulted in a finite lifetime of these magnons. We know that magnons are excitations, collective excitation inside a quantum magnetic material when the system, for example, have certain order. And these magnon excitation typically have finite lifetime. And this finite lifetime leads to a damping of these, for example, surface waves. So this is one important issue that need to be addressed in the magnon spintronics application. The second issue is about geometric dependence. So geometric dependence really depends on the nature of these magnetostatic surface wave. So for example, the typical one large family of magnetostatic surface wave known as Damon-Eschbach modes. These modes specifically live on a surface which is parallel to the directional magnetic field applied to the system. So if you look at a slightly different surface, which is not really parallel to the directional magnetic field, then these waves will easily be destroyed. So it's very sensitive to geometry of the system. So they somewhat restrict the application of the surface wave in the usual magnon spintronics. So this motivated us to think about other new revenue, new approaches to apply spintronics. So in other words, in addition to these Magnum spintronics, there are some new routes which have more robust Magnum waves, which we can use to store information and to transport information. So this is really what's behind the idea of known as topological magnetics. So the topological magnetics is a sort of make use of certain surface state in the Magnum system, which are very robust against small perturbations, such as disorder in the system. So these are spin wave devices and circuitry both are based on the known as topological magnons. So to give you a rough idea about topological magnon, let me go back to the case of topology insulator, which I believe people are more familiar with. In the case of topology insulator, you probably have seen this picture before. This picture is give you a rough idea about what happened on the edge of a two-dimensional topology insulator known as a quantum spin hole insulator. So on the edge of a quantum spin hole insulator, you have a one right mover which carries spin up, and you have one left mover which carries spin down. They propagate in opposite direction but carries opposite spins. And if the system have time Mersel symmetry in that case, these two modes cannot really backscatter with each other. So therefore, both of them are robust against basically any impurity scattering, as long as the impurity is not magnetic. So these edge states are very robust and therefore have very long lifetime. So therefore, they seem to be one route to go over the two obstacles we have mentioned earlier. Is the damping and also the dependence on the geometry of the usual magnet case. So therefore, imagine right now, if there is certain topological excitation analogous to the topological edge state in a topology insulator, but this case in a Magnon system. In other words, if we have these surface magnons which can propagate insensitive to the scattering of impurities and with a very long lifetime, these surface magnons would be an ideal carrier of information in the system, and they will provide very robust channels for us to build devices and circuitry. So this is really the basic idea of so-called topological magnetics. Is that we are looking for robust channels on the edges in such a system to serve as the building block of the devices. So recently, people have actually, for example, really proposed a two-dimensional magnetic system. And this magnetic system is based on certain theoretical model, which may actually be realized in materials such as 2D magnets. And in this system, basically the system has a property is that if you have magnetic order, which is polarized perpendicular to the two-dimensional plane, in this case, depending on the polarization of the magnetic order, if the polarization is pointing up, then on the boundary of the system, there will be a counterclockwise edge state of the magnons propagating in one way. So these are known as chiral edge magnons. And these state, because they are chiral, they propagate in one direction, so they cannot be backscattered. So they are very robust, have very long lifetime. On the other hand, if you flip the orientation of the spins, then the direction of these chiral edge channel will also be flipped. And naturally, in this case, if you instead of having a physical boundary, if you also have a domain wall between spin up region and spin down region, there is also going to be edge state on this domain wall. So therefore, in this case, we have robust channels both on the edge and on the domain walls. And because these edge channels propagate in one way, they are chiral modes, so they have very low damping and loss. They are also insensitive to the geometry of the system, and also insensitive to disorder and defects. So therefore, these are the kind of ideal carriers in topological magnetics. So this has been really proposed to be the building blocks of devices based on these magnet edge modes. So because of this motivation, then the next question we need to answer is how do we actually find these topological excitation in a magnetic material? And in particular, what is the theoretical idea behind these spin waves? And can we identify materials with these topological magnon in them. So those are the questions I want to discuss today. Of course, we won't be able to give you a full answer to all these questions, but I want to at least give you an idea about what we're after and what are the things to be done in the future. Yeah. So before going to talk about the topology inside a magnon system, I want to first go back into the case of topology insulator to emphasize actually in that case how important theory prediction has played in the discovery of topology insulator. And that can give us some idea about how we can use theory to actually help discover a new material in these for these topological magnons. So in the case of topology insulator, the best known example is also the first topology insulator that has been discovered in three-dimensional materials. That's bismuth antimony. So this discovery of this material is actually quite interesting. So there is a theory group by King and Mali, Fu, King and Mali in UPenn. So what they did is they look into actually some really old data from a international conference on thermoelectrics. This is a case where people actually study this bismuth antimony alloy, which at that time was a really hot topic for thermoelectrics. So in that case, what they have found is that in that old report, the system seemed to have a touching between different bands. So here are different lines label the energy of different bands. When two lines crosses, that means that the two band energy crosses. So to look at how these energy of the band crosses, and just based on that information, they identify a region where they believe is topological insulator. The idea is based on a concept known as band inversion. In the case of topological insulator, when two bands with different parity, for example, one band is odd under inversion, the other band is even under inversion. When these two bands crosses at certain high symmetry points, for example, at gamma point or at T point. T point is actually also a time Mersenne invariant momentum. So for any time Mersenne invariant momentum, if there is a band crossing between two bands with different parity, then they have theoretically predicted that this will lead to a transition between a trivial insulator and a topological insulator. In other words, initially, the system is a trivial insulator with no surface state. Then after this band crossing happens, it will go into a topological insulator. So just based on this very simple picture of band crossing, immediately made this prediction that there's going to be a region in this parameter space, depending on the doping, of course, in this bismuth antimony, there's going to be a finite region where you end up with a topological insulator. And that's what theory has discovered. And after that theory prediction, indeed, experimentally, people found that if you look at the surface of this bismuth antimony, you can identify there are actually 5 crossings between the surface bands and zero energy. And this is an odd number, and characterizing that the system have a non-trivial Z2 index. In other words, there are an odd number of Dirac fermions on the surface of this material. So in this example, you can see that theory actually is very, very powerful. In particular, you don't really need very complicated calculation. You just need certain information in the system. For example, whether the band has crosses at high symmetry momentum inside the Brillouin zone. Then you can make prediction whether the material is a TI or a trivial insulator. So that actually play a crucial role in the discovery of TI. So this is also very different to many discovery in condensed matter, where you first have experiments and then you have theory. But in this case, actually theory plays a driving role in this discovery. And there's also another important aspect that theory has been pushing this field forward, is that after the discovery of three-dimensional TI, theory also realizes that in addition to topological insulators, there are also many other aspects of topological phases. There are actually many different classes of topological phases. So the early discovery are the, for example, two-dimensional quantum Hall insulator, and the 2D quantum spin Hall insulator, and three-dimensional TI, which I showed in the last slides. After the discovery that a theorist has realized that in addition to these 3 different TIs, there are also other topological phases, such as topological superconductor, And of course, later people also discovered that topological semimetals such as Weil semimetals. In particular, the theory even worked out the so-called periodic table for the topological insulator and superconductors. And this table gives you an idea about if you look at different symmetry in the system. For example, the system with time-Mersel symmetry, a system without time-Mersel symmetry, a superconductor versus an insulator, superconductor with spin rotational symmetry, or superconductor without spin rotational symmetry. So if you look at the different symmetry classes, each one of them can give you some idea about what can happen in different dimensions. For example, if you look at a insulator with time-Mersel symmetry, this table shows you in 2 dimensions, 3 dimensions, there is a non-trivial insulator because this index is Z2 is not trivial. In this case, 0, it means the system is trivial. There cannot be a topological insulator. But if it's Z2, it means it can be a topological insulator in this case. If it's Z, it means there can be an integer number of different insulators in this class. So the theory actually predicts that there is a variety of topological phases inside the electronic band structure. And after this discovery of this periodic table, theory further makes the efforts to actually predict a large family of material and then catalog them. So this is some recent progress based on the idea known as topological quantum chemistry, or the so-called symmetry-based indicators. So this idea tells you that just by looking at the electronic band structure at a certain high symmetry location, such as zone center, zone boundary, or time-Mersel invariant momentum, as in the previous example of 3-dimensional TI. If you only look at if you only have information of the band structure at these high symmetry momentum, you can already make a lot of prediction on the topology of the system. In particular, the theory has been guiding the discovery of field databases. These databases catalogs different topological insulators in basically all the data in all the material which has been discovered so far, and has been, for example, studied using ab initio method. So this just tells us that in this case, the theory plays a major role, not only in the discovery of topological insulator initially, but also in the search, systematic search of the topological material that have non-trivial topology and surface states. So this really motivated us to think about the case of the magnon or spin waves. How should we understand the case of topological magnons in such approach? Meaning, the theory can guide experiments to discover new materials and then to measure property of these materials with non-trivial topological magnons. So that's really the idea behind these theoretical efforts. So for topological magnons, before I actually go into the theoretical idea, I want to first mention a few candidate materials. These candidate materials are the, I should say, most promising materials for the topological magnons. So there are many other materials that has been theoretically proposed, but have not been experimentally verified. So I did not list them. So this is really a sub list of the materials that has been measured. So these materials, the experimental probes that measure them, mostly neutron scattering spectroscopy. So what people do is that people first build theory models for these spin wave dispersions in the system. And then the inelastic neutron scattering spectroscopy can serve as a direct probe for this dispersion of these magnon. For example, here in this copper 13 BDC, this is actually known as metal organic framework material. So in this material, the copper spin 1/2 moment live on a 2-dimensional Kagame lattice. So in this system, the theory prediction is that in a 2-dimensional Kagame lattice magnet, the Dzialoszynski-Moria interaction between spins, nearest neighbor spins, can open up a gap in the spin wave spectrum at certain moment, which is k and k prime points, zone corner. In other words, same as the Dirac point in the graphing. In a zone corner momentum, Dzialoszynski-Moria interaction can open up a gap and drive the band into a non-trivial topology. In particular, the non-trivial topological bands can give rise to chiral edge state on the surface of the system. So this is what people have concluded based on this inelastic neutron scattering study. Another recent discovered material is copper telluride oxide. And in this material, people have theoretically predicted a band touching protected by time reversal and immersion symmetry in the system. And this has also been observed by inelastic neutron scattering experiment. And more recently, for the two-dimensional magnet chromium triiodide, in the ferromagnetic phase, people have also used inelastic neutron scattering to suggest that each of these magnon band, the lower band and the higher band, they have non-trivial topology in the sense that a quantity known as Chen number is non-zero for these two bands. So they suggest some edge state, which will happen, chiral edge state between these two bands. So these are the leading material in this for topological magnons. I should also make one comment is that for these materials, so far the experimental efforts has mostly been focusing on using inelastic neutron scattering to study the bulk spectrum. But I don't think there is actually direct evidence of observation of the edge state of magnon in such a system. So this is really an open question. How do you experimentally observe these edge states, which are really crucial for building magnonic devices? Okay, so after introducing this material, what I want to do next is to introduce the idea about magnons or spin waves. How should I think about it? So the idea of spin wave is the following. And think about actually a ferromagnet where spin is pointing to a certain direction. In this specific case, let's think about spin is polarized along z direction. If spin is almost polarized around z direction, it can really only vary around z direction. So the small fluctuation of spin is really the x and y component because z component is almost polarized in the system. So in this case, the low energy variable describe the dynamics of the system is really xy component. And for the xy component, we know that they satisfy the commutation relation of spins, right? Spin, if you compute commutation relation of s and sy in quantum mechanics, you get Sz. This is what characterizes spins as compared to fermion. So this commutation relation immediately leads to actually a different aspect of dynamics of the spin wave compared to electrons, for example, in a solid state material. In the case of electron, we all know, due to quantum mechanics, the time evolution of the electron wave function is governed by the Schrodinger equation. Schrodinger equation tells us if I have a Hamiltonian, H, in this case, H is a block Hamiltonian in the momentum space, HK. If I have a Hamiltonian, then Hamiltonian, which is a Hermitian matrix, can govern the evolution of the wave function psi in the system. So if I know the Hamiltonian, I know this wave function, how does it depend on time? And so on. But in the case of spin wave or magnons, because as we have said, magnon actually have a slightly different quantization condition. Like the commutation relation of the spin operator is different from the fermion operator. So therefore, if you think about the time evolution for spin wave, it behaves actually quite different from the case of block electrons inside a solid. In particular, if you write down the spin wave equation of motion, you end up with the following equation I have written down here. In particular, on the right-hand side of the formula, you can see compared to the Schrodinger equation of the block electron, the Hamiltonian H is replaced by here a matrix which is sigma y times Rk, and sigma y here is really the Pauli matrix. The second Pauli matrix is an off-diagonal matrix, 2 by 2 off-diagonal matrix. So this R is a real symmetric matrix. So there's one significant difference between this spin wave equation of motion and the block electron equation of motion suggested by Schrodinger equation is that if you look at this matrix sigma y times R, R is a real symmetric matrix. So if you take a Hermitian conjugate of this one, what you realize is that sigma y times R, this matrix which governs the spin wave evolution, this Hamiltonian is actually not Hermitian anymore. It's really a non-Hermitian matrix generally. So this is what the major difference between the spin wave evolution and the block electron. So we know the band structure and the topology of the band structure of the electronic band very well. But here we are facing a problem is that for this kind of spin wave Hamiltonian, because the matrix that governs the time evolution is not Hermitian, the structure of the topology seems to be slightly different from the electronic case. So our question is, how do I understand topological bands inside the spin wave equation motion? What should we think about it? So the idea is the following. We know the electronic band topology very well, right? So can we possibly map this problem, a spin wave problem, to an electron problem? We know electron problem, you are governed by a Hermitian matrix, which is a Hamiltonian. But in the case of a spin wave, it's actually a slightly different matrix, which is not Hermitian. So can we actually map it? So it turns out there is a trick, mathematical trick, which can do this. This trick is known as taking a square root. So if you have in this case, earlier I have said the evolution of the spin wave is governed by this matrix sigma y dot r. R is a real symmetric matrix. And more precisely, R has to be positive definite matrix. If R is a positive definite matrix, meaning the eigenvalue of the matrix R is positive. So in that case, you can take a square root of this matrix. There's a standard way to do this in linear algebra. And by taking this square root, what we can do is we can translate this spin wave Hamiltonian, which is non-Hermitian, into another matrix, which is Hermitian. So the way to do it is to use a similarity transformation. You left multiply a matrix square root of R, right multiplies inverse. This similarity transformation does not change the eigenvalue. In other words, it doesn't change the spectrum of the system, but it does make the matrix Hermitian. So therefore, in this way, we call it a Fermionization trick, is that it maps a spin wave Hamiltonian, which is bosonic, to a fermion band structure. And this is a Hermitian matrix, which is a fermion band structure. This is something we have done before. And I should also comment on this. This approach has been used previously in some other systems, such as disordered bosonic system. But the trick using those systems are slightly different from our case, in the sense that they use something known as Cholesky decomposition. As in our case, we use a square root of this matrix. So there's some advantage for this approach of taking the square root and relating this spin wave Hamiltonian to the fermion Hamiltonian. Is it maps, first of all, it maps a spin wave problem to an electronic band structure. And secondly, it preserves the symmetry. All the symmetry that exists in spin wave Hamiltonian is also preserved in the fermion band. And finally, preserve the topology of the band. In other words, if you have surface state in this spin wave Hamiltonian, you also have surface state in this fermion band. That's the advantage. So with the help of this approach, what we can do is we are able to obtain a table, not really a periodic table, but a table of topology inside a spin wave band. The reason is because we know the whole structure of the topology inside the electronic band structure. So after we are able to map the spin wave band into the electronic band, we are also able to obtain all the features in the spin wave band. Yep. So that's the idea. So in particular, I want to actually just comment on two special classes. The first one is this class with no symmetry, but in 2 dimensions. So this is a 2D magnet, for example, with strong spin-orbit coupling and also ferromagnetism. For example, I think the Chromium triode will belong to this class. So in this class, there is an integer classification. And this integer classification labels how many edge states exist, chiral edge states exist on the boundary of these 2-dimensional magnet. So for previous theoretical proposal, for example, people have proposed that paracore iridates thin film can realize this non-trivial topology, and Chromium triode is other candidate for this one. And for 3 dimension in this same symmetry class, there is a point touching in the spectrum of the spin wave. And these are known as wild magna. They are analog of the wild semi-metal in the electronic band. So these wild magna has, for example, been proposed to realize in this so-called breathing paracore lattice. So this table gives you some idea about where to look for these topological magna. In particular, you can see in these cases, if you have collinear or coplanar magnet with without spin-orbit coupling, you can see the classification is completely trivial. this strongly suggests that if you have spin-orbit coupling, it's more likely for you to end up with a system with non-trivial topological magna. So therefore, we want to actually look into material with relatively stronger spin-orbit coupling to actually identify topological magna in those systems. So in this case, it's helpful to look into the material which has been discovered so far, this copper BDC, this metal organic framework, and this copper telluride oxide, and also chromium triiodide. In this example, except for the middle one, the other two both seem to have fairly strong spin-orbit coupling in the system. For example, the Ziauloshinsky-Moria interaction is what's responsible for this case of the opening of the gap at K. And in chromium triiodide, the spin-orbit coupling is also very strong. So yeah, these are some evidences that you would want to have strong spin-orbit coupling and to favor the existence of topological magna inside a material. So here in this talk, what I'll do next is to focus on a specific type of family of material. This family is known as the MF3, or the transition metal trifluoride. So in the transition metal trifluoride, this transition metal can be chromium, iron, and cobalt. These are of interest to us. And one of the reasons we study them is because they all seem to have fairly high transition temperature. So this gives us actually an ideal platform to realize topological magnons at higher temperature, even at room temperature sometimes. So for these three different compounds, there is actually a slight difference, is that the orientation of the spin is different. For example, if you look at chromium and iron, the spin is aligned along 101 direction. On the other hand, if you look at the case of cobalt, the spin is mostly aligned along 100 direction. So these are two different axes in the system, as I will comment on very soon. So this leads to some slightly different property between iron, chromium, and cobalt. So I want to first focus on the case of chromium trifluoride. In the case of chromium trifluoride, the reason we focus on chromium is because chromium has strong spin-orbit coupling compared to iron. Because both the orbital moment and the spin moment are large. And in this case, the magnetic moment seems to be pointing along 111 direction, as suggested by this neutron scattering data previously. So in this case, first I want to actually have a quick review about the crystal structure of this material. If you look at the crystal structure, this is a perfect cubic structure. You can see that chromium trifluoride is a distorted cubic structure. You can see that these atoms are distorted from the ideal position in the cubic case. The space group in that system is R3 bar C, so it's a trigonal space group. So in particular, you have a threefold rotation axis along 111 direction. You have a twofold axis, which is in plane, perpendicular to the 111 direction. And you also have an inversion center, which is the center of every ion. Basically, every atom here, every spin here is an inversion center. In addition to these three symmetries, there is also another symmetry, which is a glide reflection plane. And this glide plane is actually shown by this plane, this purple plane here. So this glide plane includes a mirror reflection with respect to this plane, combined with a translation. And this translation is only half of translation between the A and B sublattices. So this symmetry and the C3 rotational symmetry will play most important role when we study topology of these magnon bands. So first, what I want to comment on is what does the spin wave spectrum look like in this antiferromagnetic ordered phase, the neo order phase in these trifluoride compounds. So in these trifluoride compounds, if you look into the magnon band structure, if you compute them based on certain models. So these models I should comment is obtained using symmetry analysis of the system. So we have the crystal symmetry of the system that give us the possible interaction between, for example, nearest neighbor ion, also chromium atoms in such a system. So these Hamiltonian typically include Heisenberg interaction between nearest neighbor and the easy axis interaction between nearest neighbor. This easy axis interaction is along the 111 direction because that is one special axis, a C3-fold axis in the system. There are also other spin-orbit coupling terms which I did not write on, but we do include all the possible terms allowed by symmetry. And in that case, what we have found is that there are 4 topological line nodes in the system. By line nodes, I mean the two band exactly touches along a line in the system. In particular, there are 4 lines. One is gamma A. Gamma is zone center. A is the midpoint between zone center to the corner, to the cubic corner. So along gamma A direction, there is a line node protected by 2 symmetry. One is a 3-fold rotational symmetry. The other one is a glide reflection plane. The other one is a 3 different axes along gamma B, gamma C, and gamma D. Actually, all of them lie within one of those glide planes. So these are actually protected by the glide symmetry. Let me give you some idea about why do we have these symmetry protected band touchings in the system. So the idea comes from really the representation theory of the symmetry. So for example, if we think about this glide symmetry, glide plane, the glide plane is combination of mirror reflection and translation from one side to the center of this cube. So this translation is half of the translation of the Bravais lattice translation. So in this case, what you can easily see is that the glide symmetry does not really commute with the 3-fold rotational symmetry. And here, for our 2 band in the system, they actually form the following representation of the 3-fold rotational symmetry because the 2 sublattices both sit on the 6-fold axis. So in particular, these 2 Magnon band, they carry different signature of the C3 rotation. So in this case, you can see that if you have a C3 symmetry, if they belong to different symmetry representation of the C3 due to this glide symmetry, then this 2-fold representation should be protected by both the glide and C3 symmetry. So therefore, this is why along the direction of gamma A, you have actually a degeneracy of the 2 band protected by these 2 symmetry. On the other hand, if you right now look at gamma B, gamma C, and gamma D, these 3 lines, what happened in that case is that these 3 lines lie in one of these glide planes. So if they lie in one of the glide planes, then what you can compute their glide eigenvalue. What you can show is that this glide of eigenvalue always changes sign once you increase the momentum along this direction by 2 pi. If you increase the momentum by 2 pi, the glide eigenvalue changes from plus sign to minus sign. So in other words, the band always show up in pairs inside the glide plane. So this is why we have a degeneracy somewhere on the glide plane. And in this specific case, they shows up on gamma B, gamma C, and gamma D, these high symmetry lines. So these are the idea about these band touching in the system. But as I have really said earlier, the idea about using this topological magnon to build, for example, magnetic device is to make use of the surface state of these magnon, which are chiral state, which are robust against perturbation in the system. So therefore, we want to actually look for chiral edge state rather than band touching the bulk. So how do we do that? So the idea is really the following. We already have this band touching in the bulk. What we want to do next is to add certain perturbation to the system to break this degeneracy. And in this case, generally, when you add a perturbation in the system, you break the symmetry of the system, so the symmetry is lower. When the symmetry is lower, the system generically can support a wild point of this magnon. And when you have a wild point for the magnon, you have these so-called surface Fermi arcs. And these surface Fermi arcs propagate unidirectionally. So therefore, this surface Fermi arc can serve as the protective edge state in the system. So what we want to do is to create analogs of the surface of the wild fermions in this magnon system. So the way to do it, what we have figured out, is that you can apply an electric field in the system. And this electric field would couple to the magnet through the electric dipole moment of the magnet. So typically in a magnetic system, where the low energy degree freedom are spins, the electric dipole moment typically are bilinear of spin. And here, by symmetry analysis and some perturbation theory calculation, we can obtain actually the form of the coupling of the spin system to the external electric field. So generally, this is a form of the Hamiltonian in this case. Yeah, I don't want to go to details, but the idea is really to use symmetry and to do perturbation theory based on large strong coupling expansion. So in this case, you can obtain actually you have certain exchange coupling induced by electric field, and this exchange coupling depending on the magnetic electric field linearly. And these exchange coupling, once you apply them, what you can generally show is that very generically, independent of direction of electric field in this case, as long as the electric field, for example, is not along the EZ axis. For generic direction electric field, you can see that the line node along 101 direction is still robust. It cannot be splitted. However, the other three line nodes, B, C, and D, these gamma B, gamma C, and gamma D, these three line nodes are splitted in this case. And in particular, the splitting of these two bands would lead to actually a wild point, a band touching between these two bands there. So these wild points are going to lead to surface Fermi arc in the system. So this is what happens in chromium trifluoride. And we have done a similar calculation for cobalt trifluoride. For cobalt trifluoride, the difference is that the magnetic moment, instead of along 101 direction, is along 110 direction. And in this case, a similar calculation can also yield magnon, wild magnon in such a system as shown here. Yeah. So what I want to show you in these two examples is that by applying external electric and magnetic field in other cases, you can actually engineer topological wild magnons and also surface Fermi arcs in the system. So yeah, so this is actually I think the first part of the things I want to talk about. I can see I'm already pretty late in schedule, so let me just quickly comment on the second part that I want to talk about. Quickly go through it, and then I will stop my talk and then open for questions. So the second part I want to talk about is can we actually induce interesting topology in this magnon system by driving the system with lasers? So the rough idea, the experimental setup that shows up in this situation is so-called pump probe experiment. The idea is that if first you send in some pulse with say certain periodic pulse into the system with certain frequency, and this pulse would actually generally excite the system or drive the quantum magnet by pumping energy into it. And then later, after a certain time, after this pump, you can send in another pulse to probe the system through the detector. And this actually gives us a way to drive the system out of equilibrium. So the theoretical question we want to ask here is, if you drive a quantum magnet out of equilibrium, can there be some non-trivial topology that shows up? And what can shows up in this case? So again, there is some slight difference between the electron case and spin wave case. In the case of electron, the wave function is evolved by unitary evolution operator because Hamiltonian is Hermitian. But in the case of spin wave, this evolution operator is not unitary anymore. So that's the same issue as what we are saying non-Hermitian in the spin wave Hamiltonian. So in this case, what we want to do is to couple the system with light. So again, the coupling to the leading order is electric polarization coupled with electric field. Yeah, of course, this will depend on the material, how large this coupling is. And we want to consider such a periodic drive. The frequency is given by the light. We'll ask what could happen in this case. So there's one immediate difference in the so-called Fouquet system or periodically driven system, is that the energy is not really conserved, but rather there is something known as quasi energy that's conserved. This is because if you now consider this evolution operator by one period, this is one of the most important features for this Fouquet evolution, known as Fouquet unitary. So if you look at eigenvalue for Fouquet unitary, it's not really energy which is goes from negative any real number, which can be any real number. But here the quasi energy has a period of 2 pi over t. T is a period. So this period is kind of similar to the period of a momentum in the first Brillouin zone. So that's because in this case, the time direction is periodic, just like in the spatial direction is periodic in a solid. So, so this is one of the most important features of the Fouquet dynamics. So in this case, again, our question is for the spin wave Hamiltonian is a non-Hermitian evolution. So the the evolution operator is not really unitary. So the way to understand the topology in this way is that we can use something known as a Hermitian map. We can map this this time evolution in a spin wave into a Hermitian matrix. This Hermitian matrix, again, its topology can be understood completely. And you can classify different topology in this case with different symmetries. And this is something we've been doing recently. And in particular, you can see this case in 2 dimensions. For example, you have this non-trivial integer labeled topological phase. I want to comment that this topological phase is actually quite different from the usual topological phase in static case. For example, in this case, if you consider the energy band, more precisely quasi energy band in this flocate unitary, they have 0 Chen number in the bulk, but you still have surface state going through them. So this is some intrinsically non-equilibrium topological phenomena. So what we have shown is that we have considered 2 examples. One is a 2-dimensional ferromagnet. This is quite generic. So what I've shown you is a specific square lattice example. For this 2-dimensional ferromagnet, you drive it using a light with a polarization along a certain direction, in this case, y direction, along one of the axes of the 2D system. You can end up with such a system where you have this chiral edge mode between the 2 bands. And each band, again, in this case, have Chen number 0. So it's intrinsically flocate topology in such a system. Another example is kind of related to the 2-dimensional magnet. For example, in chromium triiodide, which has been studied extensively recently. In chromium triiodide, if the number of layers is small, what people have figured out is that the system actually, the layers, although each layer is ferromagnetic, between different layers, there is antiferromagnetic order between different layers, where the number of layers is small. So in this case, what we can show is that we can again drive the system with a periodic light, and you can again get these intrinsically non-trivial topology in flocate system. And in this case, instead of having a chiral edge state, we have a helical edge state in the system. Okay, I think, yeah. So basically, I've discussed 2 types of topology. One is the topology in static magnetic order. The other one is topology in periodically driven systems. I think some interesting question in the future is, for example, what are the experimental features? What are the sharp experimental features that you can observe for this system? The other one is, can we make a systematic material search for these topological magnets? Yeah, so finally, I want to just acknowledge my collaborators, my student Yuan-Ming, and Vicky from OSU MSE, and Rolando, a faculty from OSU Physics. And particularly, I want to advertise a bit. This research is carried out under the support of NSF Marsec at OSU. We have an interdisciplinary research group working on topology and fractionalization in magnetic material. With all this, thanks for your attention.
Okay, well, thank you very much. A very interesting talk. Let's see, for the members of the audience, if you want to ask a question, please go to the Q&A button at the bottom of the Zoom screen and punch a question in there. I guess I have a question to get started, because it sounds very interesting what might be possible. Can you talk about experiments that people might be planning, or things that you could do, and where that would go in terms of something you could use to make a device or something in the future?
Oh, okay. Yeah, I think, sorry. I think you are referring to the, let me see, device, right?
Sure.
For example, magnetic, you mean device made of topological magnet, right?
Sure.
For example, yeah. So I think what people have proposed is that here we can use each of the domain as a bit, just like, typically in a magnetic drive, each magnetic domain can be used as a bit. Of course, this is a classical bit, but there is certain advantage for it. Is that you store information in the edge state of the system. So the edge state, in this case, will be chiral, and it has very long lifetime. It's magnet on the edge.
Okay.
So yeah, so that's the sort of idea. You can switch the polarization in the system, and the direction of the edge state will be reversed.
Okay.
So yeah, so that's the sort of idea.
And you could use it to transmit information too with the edge states and things
Yes.
in one place and everything.
Yeah, so idea is that if you have spin current, for example, in the system, then you can read the spin current using the so-called inverse spin Hall effect.
Okay.
Yeah. So you can use that to read out the information on the edge, and that's how you can store information.
Okay, great. Let's see. So if you want to ask a question, I'm talking to the audience now. Please type it in the Q&A on the bottom of the screen. Here we go. Gabriel Schletter, to what extent let me read it first. What extent the analogy to electronic band topology can be used? Are other topological analogs expected?
Yeah, so that's a good question. So that's really basically why we are doing this theoretical work to connect the magnon topology to electronic topology. So what we have found out is that the electronic topology, magnon topology mentioned in this work is a subclass of electron topology. So in particular, what I should say is for the magnons, if the spectrum of if the spin wave is robust, meaning if the magneto order is robust, then the magnon band cannot touch zero energy. So this is actually something different from electronic band structure. For electronic band structure, you can see you have these wild cell metal, right? So the low energy physics always happens at zero energy for electronic system. So in that case, you can have non-trivial topology at zero energy. But for magnon, the magnon band is always gapped for a stable magnetic order. So in that case, it kind of corresponds to the case of the electronic system where all the field band altogether have a trivial topology. Yeah. So in that sense, the magnon topology talked about today is a subclass of electronic topology. But there are other cases where the magnon system can have non-trivial topological property compared to electrons. One of them is this surface magnetostatic wave. So for that system, what you can see is in those systems, typically, for electronic system, when you have this surface state, the surface state is between the two bulk bands, right? At the energy between the two bulk bands, you have a surface state which connect these two bulk bands, right? So that's what typically you see the picture of the edge state. But in the case of magnon system, you can see some other case where magnon has energy higher than all the bulk bands. So on top of all the bulk bands, you can have some non-trivial magnon bands. And that's due to something intrinsic in magnonic system is that in spin system, you have this dipole-dipole interaction between spin, which is long range. And long range dipole-dipole interaction can actually induce a non-trivial, I should say, singularity at k equal to 0 in this case, because it's long range. So after you Fourier transform, you get some singularity. So that singularity can lead to this kind of weird thing where you have edge state higher than the energy of the bulk state. So that's something I did not discuss here, but that's something that's beyond the electronic band topology.
Okay, interesting. Another question, Taiki Kim, is the 2D magnetic material chemically stable or robust during the experiments?
Yeah,
experimental question.
Yeah. I think that mostly the 2D material I discussed today are the let me go there. Are these two essentially the copper BDC, this metal organic framer, and chromium triiodide. I think both of them are stable. Yeah. But for chromium triiodide, I think there is some issue about as you increase the number of layers, there seems to be a transition between the few layer case to the many layer case. The many layer case seems to be a ferromagnet, but the few layer case seems to be anti-ferromagnet. So something happened in that case. It could be structural or other things, but but chemically it's stable, I think.
Okay, last question. Time to type it in the Q&A. Okay, if not, thank you very much. Interesting stuff. Thanks very much for presenting it.
Sure.
Yeah.
Thank you.
Yeah.
Okay.
All right.
Bye-bye.
Bye-bye.